Here's something that should keep you up at night. Right now, sitting wherever you are, you're built from atoms. Carbon, oxygen, hydrogen, nitrogen, a sprinkle of phosphorus, some calcium thrown in. Now here's the peculiar part. Those atoms don't age. A carbon atom sitting in your liver right now is the exact same carbon atom it was 4 billion years ago, freshly minted inside some collapsing star. That atom doesn't develop wrinkles. It doesn't wake up with aching joints. It absolutely cannot misplace its reading glasses. And yet here you are doing all of those things. You're assembled from components that are essentially immortal, and somehow the assembly itself is not. Doesn't that strike you as deeply, wonderfully strange? Because think about it. If none of the pieces deteriorate, why does the whole machine break down? By the time we're through today, you'll have a genuine answer to that question. And the answer isn't what most people expect. It's not really about wear and tear in the mechanical sense. It's about a law of physics so fundamental that once you really grasp what it's telling you, your morning coffee will never look quite the same, and neither will your mirror. That law is the second law of thermodynamics. Let's approach it carefully because it's one of those things that sounds dry and technical until suddenly it isn't. Start with something utterly familiar. You wake up in the morning, you make coffee, you pour in some cream. Watch what happens in that cup. The cream goes in as a little white cloud. You stir it around a few times and within seconds the whole thing becomes that uniform tan color we all know. The cream and coffee have mixed completely. Fine. Unremarkable. You've seen it 10,000 times. But now ask yourself something you've probably never seriously asked. Why doesn't it ever run the other direction? Why have you never stirred your coffee and watched the cream gather itself back up into a white blob while the rest of the liquid turned dark again? You haven't. Nobody has. In the entire history of the cosmos, cream has never unmixed from coffee by stirring. Not once. Why? You might shrug and say, well, things just mix. They don't unmix. That's obvious. But that's not explaining anything. That's just saying the same thing twice with different words. The real question is why, and here is where it gets genuinely astonishing. If you could zoom in and watch the individual molecules bouncing around in that coffee cup, every single collision between every single molecule is perfectly reversible. Take a film of two molecules bouncing off each other and run it backwards. It looks completely fine, totally legal. Newton's equations don't have a preferred direction for time. Forward and backward are equally valid as far as the fundamental laws are concerned. There is no built-in arrow in the physics of atoms, and yet, when you assemble billions upon billions of those atoms together, suddenly there's an enormous difference between past and future. Cream mixes forward, hot coffee cools down, but never spontaneously heats back up. Eggs shatter, but never reassemble. You grow older, but not younger. Where does this one-wayness come from when the underlying rules are perfectly symmetric? That is the question. That is what the second law is genuinely about, and it is precisely why your body eventually gives out. Let me show you something I used to do with students. I'd play them a film of a pendulum swinging, then run the same film backwards, and ask them to tell me which version showed time going forward. They couldn't. A swinging pendulum looks identical whether time runs either direction, perfectly symmetric. Then I'd show them a glass falling off a table, hitting the floor, and shattering. Forwards? Completely normal. Backwards? 1,000 shards magically leap off the floor, fly upward, and assemble themselves into a perfect glass that lands gently on the table. Everyone laughs. It looks ridiculous, like something from a cartoon. But here's what I need you to understand. There is nothing in the laws of physics that actually prohibits that. Every collision between every shard of glass and every air molecule, if you reverse them all simultaneously, would be perfectly legal. The reassembling glass is a physically possible event. It just never happens. Why not? Let me give you a situation that makes the answer visible. Imagine a box with a divider down the middle. Left side, red gas, right side, blue gas. Same temperature, same pressure, everything balanced. Now you pull out the divider. What happens? The gases mix. After a little while, you've got purple gas evenly distributed everywhere. Boring, uniform, thoroughly mixed. Now here's my question. Every red molecule is just bouncing around obeying Newton's laws. Every blue molecule is doing exactly the same. Every collision is reversible. So why doesn't the purple gas ever spontaneously separate back into red on the left and blue on the right? The answer isn't that it's forbidden. This is the crucial point. There's no law that says it can't happen. The reason is that it's so fantastically, almost incomprehensibly unlikely that for all practical purposes, it might as well be impossible. Let me show you the arithmetic. Suppose you have just 10 molecules, 5 red and 5 blue. Pull out the divider, and at any moment each molecule can be on either side. How many possible arrangements are there? Each molecule has 2 choices, so the total is 2 multiplied by itself 10 times. 2 to the 10th power, which is about 1,000 arrangements. Out of those 1,000, exactly 1 has all the reds back on the left and all the blues on the right. So the probability is 1 in 1,000. Not great odds, but if you were patient enough, you'd eventually see it happen. Now make it realistic. A mole of gas contains roughly 6 times 10 to the 23rd molecules, Avogadro's number. The number of possible arrangements is now 2 raised to the power of 6 times 10 to the 23rd. I want you to appreciate how enormous that number is. It dwarfs the number of atoms in the observable universe. It dwarfs anything you've ever tried to imagine. And out of all those arrangements, only a vanishingly tiny sliver have all the red molecules neatly on one side. If you waited for the spontaneous unmixing of a mole of gas, you could sit there for the entire age of the universe, then do it again 1 trillion more times, and you would never see it happen. Not once, not even close. So unmixing isn't illegal. It's just so improbable that the distinction between impossible and hasn't happened yet in the entire history of everything becomes meaningless. That is what the second law of thermodynamics is actually saying. It's a statistical statement, not a fundamental prohibition. It says that systems drift from less probable arrangements toward more probable ones, for the simple reason that there are vastly more of the latter. It's not a mysterious force. It's just counting. We need a word for what we're counting. That word is entropy. Entropy is a measure of how many different microscopic arrangements of a system are consistent with what you'd observe from the outside. Let me make that concrete with an analogy. Take a deck of 52 cards. I ask you to sort it perfectly. Spades first, then hearts, then diamonds, then clubs, each suit running ace through king in order. How many arrangements satisfy that description? Exactly 1. Now I say, make it random. How many arrangements count as random? Well, the total number of ways to arrange 52 cards is 52 factorial. That's approximately 8 times 10 to the 67th, an almost unthinkable number. So if you start with the sorted deck and shuffle it, you're essentially guaranteed to land on something that looks random, because virtually all possible arrangements look random. And if you start with a random deck and keep shuffling, the chance of landing on the perfectly sorted arrangement is about 1 in 10 to the 67th. You could shuffle for longer than the universe has existed and never see it. The sorted deck has low entropy. There's only one way to be sorted. The shuffled deck has high entropy. There are an astronomical number of ways to be shuffled. The second law says you drift from low entropy to high entropy, not because something is pushing you there, but simply because high entropy is where almost everything is. You wander through the space of possibilities, and almost everywhere you look, it's disordered. That's all. Now let me push this analogy a little further because it opens up something important. Think about what it means to describe the state of each deck. A sorted deck is easy to describe. You can tell someone its complete configuration in just a few words. It's perfectly ordered. Done. Very compact description. But to describe a shuffled deck exactly, you'd have to list all 52 cards in sequence. Much more information required. The shuffled deck has high entropy, partly because specifying exactly which of the gazillions of shuffled arrangements it happens to occupy requires a great deal of information. There's a deep connection here. Entropy and information are intimately related. Low entropy means ordered, predictable, easy to describe. High entropy means disordered, random, informationally expensive to specify. When information is lost, when you stop knowing where the cards are, entropy rises. And this connection between information and entropy is going to matter very much when we talk about what aging actually is, because aging is, in a real sense, a degradation of information. The specification of where everything should be in your body gets noisier over time. The patterns blur. The instructions get harder to read. But let me not get ahead of myself. What does all of this have to do with you growing older? Think about what you are from a physics perspective. You're a specific arrangement of roughly 7 times 10 to the 27th atoms, 7 billion of them. And these atoms aren't randomly scattered. They're organized into enormously specific patterns. Proteins folded into precise three-dimensional shapes. DNA coiled into chromosomes with billions of base pairs in a specific sequence. Membranes, organelles, cells organized into tissues. Tissues into organs. You are, thermodynamically speaking, a low-entropy system. You are like that perfectly sorted deck of cards. And the second law is pressing on you constantly, relentlessly, always nudging you toward becoming more like a shuffled deck. But wait, if entropy always increases, how did you get organized in the first place? How does a low-entropy arrangement of atoms arise at all? That's a wonderful objection. And the answer is that you're not a closed system. The second law says entropy increases in isolated systems, systems that don't exchange anything with their surroundings. But you eat, you breathe, you radiate heat. You're constantly trading matter and energy with the rest of the universe. And here's the elegant trick life has found. You absorb low-entropy material from your environment. Organized molecules like sugars, fats, proteins, extract the useful energy in them, maintain your own organization with that energy, and then export high-entropy waste back out. Carbon dioxide, heat, other byproducts. Your internal entropy doesn't have to increase as long as you're generating enough entropy in your surroundings to more than compensate. Think of a refrigerator. A refrigerator decreases the entropy inside itself, makes things colder, more ordered. But it does this only by pumping heat out the back, warming the room, increasing entropy there. The total entropy of refrigerator plus room still goes up. The refrigerator just relocates the disorder. You do the same thing. You're a machine that takes in organized matter and puts out disorganized waste. And the energy difference keeps you running, keeps you ordered. You eat order and excrete disorder. That, at the most fundamental level, is what metabolism is. Let's make it concrete. You eat an apple. The apple is a beautifully organized collection of sugars, fibers, vitamins, relatively low entropy. Your digestive system dismantles those complex molecules into simpler ones. Glucose, amino acids, fatty acids. The released energy gets captured as ATP, the cell's energy currency. That ATP gets spent on building proteins, repairing DNA, contracting muscles, firing neurons, all the processes that maintain the intricate organization that constitutes you. And the waste products, glucose combines with oxygen and becomes carbon dioxide and water. Simpler molecules, higher entropy. Out through your breath and your kidneys they go. The full accounting, low entropy apple and oxygen go in. High entropy, carbon dioxide and water and heat come out. And in the middle you stay organized for another day. You're a machine that converts structured food into disordered exhaust and uses the difference to maintain yourself. Schrödinger, the quantum physicist, captured this beautifully. He observed that what an organism feeds on is essentially negative entropy, that life's trick is to extract order from its surroundings. But here's why you still age despite all this. You can fight entropy for a while. You can maintain your proteins, repair your DNA, replace worn-out cells. But you cannot fight it forever. And here's the deep reason why. Every act of maintenance, every repair, every process of upkeep requires free energy. Using that energy means degrading some organized low-entropy energy source into disordered heat. And there are always losses. The repair machinery itself, the molecular machines that fix damage, those machines are made of molecules that also get damaged. The systems that repair those systems get damaged too. It's maintenance all the way down, and at every level, errors creep in. The repair is never perfect. Imagine photocopying a page. First copy looks great. Copy the copy, still fine. But copy the copy of the copy of the copy 100 times, 1,000 times, and eventually the text becomes unreadable. Errors accumulate. That's what's happening in your body continuously at the molecular level. Your DNA gets hit by radiation, by free radicals, by random thermal jostling. Your repair enzymes catch the vast majority of it. You have dozens of distinct repair systems with lovely technical names like base excision repair, nucleotide excision repair, mismatch repair, double-strand break repair. They're constantly proofreading, patching, correcting. But not everything gets caught. Maybe one error in a billion survives the repair process on any given day. Sounds tiny, right? Multiply that by trillions of cells over decades of days, though, and you're accumulating billions of errors. And those errors compound. Damage to a repair enzyme makes that enzyme less effective, which lets more damage through, which impairs more repair enzymes, which lets through even more damage. A slow cascade. This matches what biologists call the disposable soma theory. Evolution didn't build you for immortality. Evolution built you for reproduction. From natural selection's perspective, it's more efficient to construct a body that functions well long enough to reproduce and raise offspring. Then let's go. Than to build one that runs perfectly forever at enormous ongoing cost. If you wanted a car that lasted 1,000,000 years, you could build one. Better materials, more redundancy, more sophisticated maintenance. But it would be extraordinarily expensive. Building one that lasts 20 years and gets the job done is much cheaper. Your body is the economical solution, adequate for reproduction, and after that, well, from the genes' perspective, you were just a temporary vessel anyway. Harsh, but that's the logic of natural selection, and it fits perfectly with what the physics of entropy is telling us. And even if your repair mechanisms were flawless, which they aren't, running them would still consume free energy, and consuming free energy still produces entropy elsewhere. You cannot run the maintenance operation without generating disorder downstream. The math doesn't permit it, so here's the deep truth. You don't age because your atoms deteriorate. Your atoms are fine. You age because maintaining order, resisting entropy, is a battle you can win for a while but never win permanently. The errors accumulate. The repair systems weaken. The organization frays. Eventually entropy wins. You return to equilibrium, your atoms dispersed back into the world to be borrowed by other organisms, other temporary pockets of order, fighting the same inexorable law. Now, before we go further, let me address a misconception I hear regularly. People learn about entropy and the second law and say, aha, then evolution is impossible. How can life get more complex over time if entropy always increases? Surely you can't get more organized without violating the law. This is a misunderstanding, and it confuses local entropy with global entropy. Consider a pot of water heating on a stove. Turn up the heat, and what happens? The water organizes itself into convection cells. Hot water rises in the center, cools at the edges, descends, gets heated, rises again. You get beautiful, structured, repeating patterns of circulation. Hold on, I just told you entropy tends toward disorder, but here the water is spontaneously organizing itself. What gives? The answer is you have to look at the whole picture. Yes, the water is becoming more ordered, but the stove is burning fuel and generating substantial entropy. The water is radiating heat into the room, generating more entropy still. Add it all up, and the total entropy of stove plus water plus room is definitely increasing. The water can become locally organized precisely because it's exporting entropy to its surroundings faster than it's creating order within itself. This is a general principle. Whenever you see order spontaneously emerging anywhere, look for where the disorder is being exported. A hurricane is a magnificently organized structure. Spiral bands, a defined eye, structured wind patterns. That organization comes from the thermal energy of warm tropical ocean water, which the hurricane disperses into the upper atmosphere. The hurricane is essentially a machine for moving entropy from warm ocean to cold sky, and the beautiful spiral is a byproduct of that process. A snowflake is an exquisitely symmetric crystal. Where does that symmetry come from? When water vapor freezes, it releases latent heat into the surrounding air, increasing that air's entropy. The snowflake's stunning order is paid for by the disorder it creates around it. Evolution works the same way. It's powered by the sun, which is a colossal source of low entropy energy. The sun fuses hydrogen into helium, releasing high-quality electromagnetic radiation. That radiation reaches Earth. Plants capture it and use it to build organized molecules out of carbon dioxide and water. Animals eat the plants. The entire biosphere is a vast engine driven by a continuous river of low entropy energy flowing from the sun, with high entropy waste heat radiating back out into the cold of space. Life on Earth can become more complex over billions of years because we're not an isolated system. We're connected to that stellar energy source. We're riding the current of negative entropy, as Schrödinger might have said. Life doesn't struggle against the second law. Life exploits it. Life is what emerges when matter finds a way to channel the universal drift toward disorder through self-replicating, self-maintaining patterns. We're not exceptions to the laws of physics. We're consequences of them. But even the sun is spending down its account. It's converting nuclear fuel into energy, and eventually that fuel runs out. In about 5 billion years, the sun will exhaust its hydrogen, expand into a red giant, then collapse into a white dwarf. And on the largest scale, the whole universe is running the same process. All the stars are burning, radiating energy into the void. In the very far future, we're talking unimaginably long timescales, all the useful energy gradients will be gone. The universe will reach maximum entropy. Every region will be the same temperature. Nothing will be able to happen. This is sometimes called the heat death of the universe. What do I mean by nothing happening? Not that the universe will be empty. There'll still be particles, still be space. But without temperature differences, without gradients, without flows, no work can be done. Think about a waterfall. The water at the top has potential energy and can do useful work on the way down. Turn a mill wheel, drive a generator. But once it's in the still pool at the bottom, it can't do anything more. It's at equilibrium. The heat death of the universe is like everything being permanently in that still pool. All the energy is still there, but it's spread so uniformly that there's nowhere for it to flow, nothing for it to do. It's a melancholy thought. Trillions upon trillions of years from now, when the last stars have extinguished, when even the black holes have evaporated through Hawking radiation, when everything is settled to the same temperature, the universe will be done. Not empty, just finished. Nothing happening, nothing able to happen, maximum entropy, perfect stillness. But here's what I want you to take from that. We exist in a remarkable moment. The universe began in an extraordinarily low entropy state, for reasons we don't yet fully understand, and has been moving toward higher entropy ever since. During that long journey from order toward disorder, interesting things can happen, structures can form, life can arise, you and I can exist. We're like small whirlpools in a flowing river. The river flows from the mountains toward the sea, from low entropy to high, and we're temporary vortices that form along the way. Brief, yes, but real and beautiful. So in the longest view, entropy wins. It always wins. But that's not cause for despair. It's simply the nature of things. And in the brief cosmic interval we call a lifetime, we get to be here. We get to be these improbable, temporary, astonishing arrangements of matter that are somehow capable of thinking about themselves and asking why. Let me pause and tell you about a famous thought experiment that puzzled physicists for nearly 100 years. Maxwell's demon. James Clerk. Maxwell, who worked out the complete equations of electromagnetism, proposed this. Imagine a box of gas at some uniform temperature. The molecules are flying around in all directions, some fast, some slow. Temperature is just the average of their speeds. Now imagine a tiny, intelligent creature, the demon, sitting in a hole in the middle of the box with a small trapdoor. When the demon sees a fast molecule approaching from the left, he opens the door and lets it pass to the right. When he sees a slow molecule approaching from the right, he lets it through to the left. He doesn't push the molecules or do any mechanical work. He just operates the door at the right moments. After a while, all the fast molecules are on the right, all the slow ones on the left. The right side is hot, the left side is cold. You've produced a temperature difference without expending energy, but that should be impossible. The second law says you cannot decrease entropy without doing work, and heat does not spontaneously flow from cold to hot. This puzzle went unresolved for decades. The answer, finally worked out in the 20th century, is subtle and lovely. The demon has to observe each molecule, has to gather information about whether it's fast or slow. And gathering information requires physical processes. Every observation has to be stored somewhere, in the demon's memory or some equivalent. And here's the key. When that memory fills up and the demon has to erase old observations to make room for new ones, the erasure itself generates entropy. Erasing one bit of information produces at least k times the natural log of 2 in entropy, about 10 to the minus 23 joules per Kelvin. Tiny, but not zero. The entropy the demon generates through information processing is at least as large as the entropy reduction he achieves through sorting. The second law holds: the demon can't cheat. And here's why I'm telling you this. Your body is Maxwell's demon, constantly observing, constantly sorting. Your enzymes recognize specific molecules and catalyze specific reactions. Your immune system distinguishes self from foreign invader. Your DNA repair machinery detects lesions and corrects them. All of this is information processing, and information processing generates entropy. Your body is swimming upstream against the entropic current, using information to maintain order. But every time it processes information, it dumps more disorder somewhere downstream. Aging is, at a deep level, the accumulation of information loss. The signals get noisier, the patterns get harder to distinguish from the background, the sorting gets less precise. Eventually the noise overwhelms the signal, and the organization collapses. Let me give you one more image to make this vivid. Imagine a jigsaw puzzle, 1,000 pieces assembled perfectly into a beautiful landscape. Mountains, a lake, the works. Now I shake the table, gently, once a day. After the first shake, one piece is slightly out of place. You nudge it back. Trivial. After 100 shakes, several pieces need repositioning. You spend a few minutes on repairs, still manageable. After 1,000 shakes, pieces have migrated significantly. You spend an hour restoring things. You notice the edges of some pieces are getting worn, slightly frayed. Your repairs are almost as good as the original, but not quite. After 10,000 shakes, large sections are scrambled. You spend all day fixing what you can. Many pieces no longer fit together cleanly. The picture is losing definition. After 100,000 shakes, you're spending more time on repairs than on anything else. The puzzle is more patched than original. Significant sections no longer connect properly. The image is barely recognizable. And eventually, inevitably, comes the shake you cannot recover from. The puzzle is gone. What remains is a box of worn, disconnected pieces. That's aging. The daily shakes are thermal fluctuations, radiation strikes, chemical accidents. The repairs are your enzymatic machinery, your immune system, your cellular maintenance systems. The wearing of the pieces is the accumulated damage your repair systems couldn't quite correct. Now let me bring in the mathematics, just enough to show you how elegant this all is. The key equation is Boltzmann's formula. S equals K log W. S is entropy. K is Boltzmann's constant, a tiny number that bridges the microscopic world of atoms to the macroscopic world of temperature and pressure. And W is the number of microstates. What's a microstate? It's a complete specification of what every particle in the system is doing, its precise position, its exact velocity, everything. A macrostate is what you can measure from outside: temperature, pressure, volume, that sort of thing. Many different microstates can produce the same macrostate. If I tell you a gas is at a particular temperature and pressure, there are an astronomical number of different particle arrangements that would give exactly those measurements. W counts all those arrangements. Entropy is the logarithm of that count. Why the logarithm? It's a beautiful mathematical choice. Suppose you have one system with W1 possible arrangements and another independent system with W2 possible arrangements. The combined system has W1 times W2 total arrangements. For each arrangement of the first, you can have any arrangement of the second. But we want entropy to be additive. The entropy of 2 cups of coffee should be twice the entropy of 1 cup. The logarithm gives you exactly that, because the logarithm of a product equals the sum of the logarithms. Log of W1 times W2 equals log W1 plus log W2. Total entropy equals the sum of the parts. Boltzmann knew exactly what he was doing. He was so proud of this formula S equals K log W, that he had it carved on his tombstone, and justifiably so. It's one of the most profound statements in all of physics. It connects the microscopic world of atoms to the macroscopic world of heat and irreversibility. It explains why time has a direction. It explains why coffee cools, why eggs break, why you age. And it accomplishes all of this just by counting, by asking how many ways things can be arranged. No mysterious forces, no exotic physics, just probability. Now, living systems have a specific thermodynamic character. We're what physicists call dissipative structures. We exist far from equilibrium, and we maintain our organization by continuously dissipating energy, continuously generating entropy, and shipping it out to our surroundings. A candle flame is also a dissipative structure, in its simpler way. It has shape, it has structure, but it only persists as long as there's fuel and oxygen. Remove the fuel, and the organization vanishes. You're the same in principle, just enormously more intricate. Cut off the food and air and water, and the organization breaks down. Your atoms rejoin the environment. The difference between you and a candle is complexity. The flame maintains a simple structure through a simple reaction. You maintain an extraordinarily complex organization through thousands of simultaneous processes: DNA replication, protein synthesis, cell division, immune response, neural signaling, all requiring energy, all producing entropy. And the more complex the organization, the more ways there are for things to go wrong. The more damage accumulates. The more exposed you are to the creeping disorder of entropy. A crystal can persist for billions of years because there's simply not much that can go wrong. The atoms are locked in place by strong bonds, but you're not a crystal. You're dynamic, far from equilibrium, extraordinarily complicated. Your proteins aren't locked in place. They're jiggling, folding, unfolding, interacting. Your cells are dividing and dying and being replaced. There are so many more ways for you to be disordered than properly organized. That's why entropy catches up with complex organisms in decades while rocks endure for eons. Consider your genome: 3 billion base pairs, each one capable of being one of 4 possible nucleotides, encoding the instructions for building and running you. The number of possible genomes is 4 raised to the power of 3 billion. That number is larger than the number of atoms in the observable universe, raised to the power of the number of atoms in the observable universe. Out of all those possible sequences, only a tiny fraction would produce anything living. Most random base pair sequences produce nothing viable at all. Your genome is a needle in a haystack of unimaginable dimensions. Maintaining that needle, copying it accurately when cells divide, repairing it when it gets damaged, that's the central ongoing challenge of being alive. And the longer you do it, the harder it gets. The copies get noisier. The repairs get less precise. The needle slowly blurs back into the haystack. Now here's something I want you to hold on to, because it's easy to misread what all this is saying. You might conclude that the universe is hostile, that entropy is our adversary, that physics is conspiring against everything we value. That would be exactly wrong. Entropy is not your enemy. Entropy is what makes you possible in the first place. If the universe were already at maximum entropy, if everything were in equilibrium, nothing would ever happen. No gradients, no flows, no change. The universe would be perfectly, permanently dead. It's precisely because the universe began in a low entropy state that anything interesting could ever occur. The flow from that initial order toward maximum disorder is what drives everything, and life rides that flow. Life captures free energy from that gradient and uses it to build, to organize, to persist. Without entropy, without the second law, without that universal drift from order toward disorder, there would be no life at all. There would be no us. So entropy isn't the current we're fighting against. Entropy is the current that carries us. We exist because of it, not in spite of it. And yes, eventually that current reaches its destination. Eventually entropy catches up with all of us. But the journey, the brief, improbable, gorgeous journey, that's the whole point. People sometimes ask, if everything falls apart in the end, if entropy is patient and inevitable, what's the point of anything? And I always want to say, you've got the question exactly backwards. The point isn't some final permanent state. The point is now. The point is being here, being alive, being capable of understanding even a fraction of how the universe operates. We have a deep tendency to associate meaning with permanence. If something doesn't last forever, it doesn't really matter. That's the logic, isn't it? But think about a flower. It blooms beautifully for a few days, then wilts. Should we conclude flowers are meaningless? Should we stop growing them because they don't persist? Of course not. The flower is beautiful during its brief window. Its impermanence is part of what makes you notice it, part of what makes you pause, or consider a symphony. The notes ring out and then the air goes still again. Did the symphony not matter because it ended? The experience was real. The beauty was real. The ending doesn't undo the fact that it happened. Life is the same. You are made of atoms forged inside dying stars. You are arranged in patterns that 4 billion years of evolution developed and refined. You can contemplate your own existence, reason about the laws that govern your own mortality, feel wonder at the improbability of your own presence. That is astonishing. That may be the most astonishing thing anywhere in the observable universe. And yes, it's temporary. Everything is temporary. But a sunset doesn't need to last forever to take your breath away. A piece of music doesn't need to play for eternity to move you. Love doesn't need to be immortal to be real. The impermanence isn't a defect. The impermanence is part of what makes it precious. Sometimes I try to imagine what existence would be like in a universe at maximum entropy. Everything at the same temperature. Nothing happening. Perfect equilibrium. It sounds like death, because it is. No change means no life. No gradient means no possibility. Complete stasis. We don't live in that universe. We live in the interesting one. The one where gradients exist, where energy flows, where complex structures can assemble and hold together for a while before dissolving back into the general disorder. And that, for a while, is everything. That's the whole story. Universe starts ordered, ends disordered, and in between, there's us. There's life. There's consciousness. There's everything that makes existence worthwhile. Entropy is not your enemy. Entropy is your teacher. It teaches you that time is real, that moments are finite, that everything you have is temporary and therefore precious. Every second you're alive, you're engaged in a battle against the most fundamental tendency of the universe. And for a few extraordinary decades, you win. You think, you feel, you love, you wonder. And then eventually, the tide comes in. So don't resent entropy. Understand it, and then go live your brief, improbable, beautiful, low-entropy life as fully as you possibly can. That's what physics offers us. That's the lesson of thermodynamics. Not despair, appreciation. Your atoms don't wear out, but the arrangements keep shifting, the probabilities keep rolling, and entropy, patient, universal, mathematically inevitable, claims everything eventually. Just not today. Today you're still here. Still organized, still fighting the magnificent, doomed, and entirely worthwhile fight against disorder. So go use that organization while you have it. Now I'm genuinely curious, having thought through all of this together, does grasping the physics underneath aging actually shift something in how you experience being alive? Or does it mostly just make you want to go get that cup of coffee?